applying force to an object, and you've seen them in things, whether you know it or not. There are springs in beds, usually, or in chairs, things of that nature. Uh, and the springs are also something that used to be in scales, like bathroom scales. I don't know if they still are anymore, but they used to be in bathroom scales, commonly used to measure weight. Now a spring, we kind of model by making a little squiggly line. We got a mass attached to the spring, then there it is. If we compress the spring, if we push it down, the spring exerts a force, which I will call capital F sub S for spring force, using a capital F to distinguish it from static frictional force. If we stretch the spring out further, it will also exert a restoring force. So spring force always points backward toward equilibrium. Springs have an equilibrium length. For this case, I'll call it x equals 0. Right? And if a spring is moved from this equilibrium length, it will exert a force that points back toward equilibrium. And that force is denoted by F equals minus kx. This is known as Hooke's law for springs. This k is called the spring constant, as units of newtons per meter, and it has to do with the geometry of the spring and the material it's made out of. So how tightly it coils, how fast it'll snap back. And this, I guess technically this should be a delta x. The minus says that it's a restoring force. You notice here that if this is a positive x displacement from equilibrium, and that positive x leads to a negative force, the force goes back to the left. And likewise, if this is a negative x displacement from equilibrium, then that exerts a positive force. So that's where the sign comes from. That's just indicating that it is a restoring force. And as you can see, the restoring force is proportional to the distance from equilibrium. Right? So we can do all kinds of problems with this. The simplest being, if you're given a force and a displacement from equilibrium, you can calculate the spring constant. You're given a spring constant and a distance, you can get a force. Given a spring constant and a force, you can calculate the distance from equilibrium. And so that's all pretty simple. 1 kilograms hangs from a vertical spring, causing the spring to stretch 15 centimeters from equilibrium. So we got a spring, and there's a mass hanging from it, and the spring is stretched 15 centimeters from equilibrium. Well, what forces are acting here? We've got gravity, and then we've got spring force going upward, which is k delta x. The minus, don't necessarily just plug in the minus. Give the sign you give to this is going to be based on the direction that force is pointing. Since it's stretched, that force is pointing upward, and therefore we'll give a positive sign to the kx, even though the formula says minus kx. So this is pretty simple. It's just hanging there. So the sum of forces in the y direction is 0. We have a force of kx going up. We have a force of mg going down. So, and then my question is, what is the spring constant? And so we can simply plug in k times 15 centimeters is 0.15 meters equals, if we move the mg over, 1.1 times 9.8. So plugging that in, 1.1 times 9.8 over 0.15 gives us a spring constant of 71.866666, repeating, call that 0.867 newtons per meter. Right? It's a pretty simple application of our problem. I can make it more complicated. To 2 springs, 1 on each side. The box has mass 13 kilograms. Each spring is constant 37 newtons per meter. The coefficient of static friction between the box and the floor is 0.62. How far can the box be displaced from equilibrium and remain at rest? So what's going on here is we've got a box And this box is attached to 2 springs on either side of it. Alright. Now, if we move this box to the right, this spring is going to be compressed and exert a leftward force. This spring is going to be stretched and also exert a leftward force. So, on each, let's assume it's displaced to the right, we have a spring force over here, we have a spring force over here, they're identical. So the sum of the forces in the x direction, if it remains at rest, the sum of the forces in the x direction is 0, and that's equal to, we've got minus 2 spring forces going on to the left, and then in the other direction we have static friction. Okay. Now, how far can it be displaced from equilibrium and still remain at rest? We're looking for the furthest distance, which means we're looking for the maximum. We want to hit that maximum value of static friction, which is mu sub s times normal force. In the vertical direction, there's only normal and gravity, so this is mu sub s times mg. And so we can say that 2kx equals mu sub s times normal force, which is equal to mu sub s times mg. And if we rearrange that, we get that the distance we can be displaced from equilibrium is us mg over 2k. And then we can plug in values 0.62 times, where's the mass of the box? 13, 9.8 over 2 times 37. And if we plug that in, 0.62 times 13 times 9.8 divided by 2 times 37 comes out to 1.067, etc. meters. So that's an example of a more complicated problem I could do with springs. And really, I can insert a spring into any of the types of problems we've done so far, and then you could solve it and work it out using Hooke's law.